Triple integrals in spherical is a little bit more challenging than it was in cylindrical, because really cylindrical was just polar with a z direction. So it was pretty easy to figure out what a small piece of volume would look like there. However, a small piece of volume in spherical is a little bit harder to do, and a picture is not something I'm good at drawing. So you may want to look at your book for this picture. But the idea is, remember, in spherical we have three different directions we move. We move on a row or a radius out. We swing in the xy plane some distance theta, and then we move up and down some angle phi from the z-axis. So if this is our z-axis, this is x and this is y, imagine if we did a little bit of each one of these movements, we'd get this little wedge kind of cut out here. So what is the volume of that wedge? Well, the side coming from the origin out, that would be that side right there. That's just a little piece of rho, right? That's just as we change coming from the origin out. Now the other two sides are the sides of kind of the top and the bottom of this little shape. The easiest one to see is the one that swings in the xy plane. So either the bottom or the other side of this, the top, wrong side of this. Let's look at this side. Let's do this first, that would be a little bit easier. All right, this side is the amount that we're coming down from the z-axis. So the amount that we're coming down from the z-axis is just the change in d phi. Now, unfortunately here, remember, that's an arc length there. So the arc length would be rho d phi, just like we did the arc length when we did a small piece in polar. Now this piece, the one I drew the arrow to wrong last time, this side's a little bit more difficult. This is still going to be an arc length, so we're going to have a rho, wrong color, and whatever. We're going to have a rho d theta because we're swinging in the theta direction. But also, if you can kind of see, I know it's tricky, as we get farther away from the z-axis, this starts to spread out, which means that changes the farther down that we go in this angle phi. Now, since it's kind of think about this as a right triangle, you think about that as the opposite side. This also has a sine of phi in it. So this side's the most complicated side. Let me actually put that in red too then, I guess. This was rho d phi. So the volume of this is kind of a little rectangle. So a small piece of volume would be length times width times height. So we multiply all three of these together. What we end up with is rho squared sine phi. And the order that we generally do this is d rho, d phi, d theta. And that's pretty standard in the order that we are going to try to integrate this. So we get this extra conversion bit here, again, because you can see as we move farther away from the origin, this little volume element actually gets bigger. So this is the scale to keep it the same as we go from rectangular to spherical. All right, let's try just a couple of problems here because this is a little bit more difficult than what we've seen in the past. We got to remember that this is our volume element. Let's do the most classic problem that you'll ever see when it comes to spherical, and it's called the ice cream cone problem. You'll see why in a second. Let's say find the volume between, let's go, z squared is equal to x squared plus y squared, and z is equal to square root of, I don't care, 25 minus x squared minus y squared. All right, so to do this, it would be helpful if we knew what this actually looked like. So let's see if we can set this up. Now the easiest of these two graphs is probably this one. This is just a hemisphere, the top half of a sphere of radius 5. So what we'd end up with here is this dome shape. Act like that's a hemisphere, not a gumdrop. All right, now this here, this looks almost like our paraboloid, but it's not because the z is squared. What this is our cone. Now that actually has a top in the bottom to the cone. But if you notice, since we're only using the top half of the sphere, we're only looking at this top piece. So if you kind of broke this out, you can see why this is the ice cream cone bottom. Because the bottom gives us a cone, and the top is our sphere. Now, I over-exaggerated the top there, but you can kind of see that that's what we would get. So let's see if we can come up with the triple integral for this in spherical. Let's get our ice cream cone out of there. So for our triple integral, we know that our little piece of volume is going to be rho squared sine phi. Let's do d rho d phi theta. Okay, so what does rho come from in this entire region? Well, you got to picture every single time that we leave the origin and we go out, what do we hit? Well, since we're in this cone region, every time we go out, we kind of go up and we always hit the hemisphere at the top of this cone, right? Anytime you leave the origin and you go out, you're always hitting the hemisphere. So that's just what? Rho equals 5. So this just goes from 0 to 5. All right, what does phi run from? Let's just take a look at a cross section. Sometimes that's a little bit easier to see. Remember, our ice cream cone kind of looks like this. What does phi run from? Well, phi runs from the z-axis down. That's what phi is. Well, it's going to go from phi equals 0, that's starting at the top, down to whatever that angle there is. So how do I figure out what that angle is? Well, that's where both curves meet each other. So that's when z squared equals x squared plus y squared meets this. Or if I rearrange this, here's our two curves. We know that z squared is equal to x squared plus y squared. If I just write this more as a sphere, x squared plus y squared plus z squared is equal to 25. Now remember, I got to keep in the back of my mind that when I change it to this form, we're not using the whole sphere. We're only using the top half of the sphere, or where the z's are positive. We'll use that in a second. So I need to know where these two are equal to each other so we can solve this system of equations. Probably the easiest way to do this is, what do we have here? We know z is equal to x squared plus y squared, so I can replace this entire x squared plus y squared over here with z squared equals 25. So I get 2z squared is equal to 25. Z squared is equal to 25 over 2. So z is equal to plus or minus when we take the square root. But remember, we're only talking about the top half of the sphere, so we're only going to use the positive, square root of 25 over 2, or 5 over the square root of 2. Now, what does that actually tell me? What did we just figure out here? That actually tells me the height that these two meet each other. And this is 5 square root of 2. Well, how is that helpful to us? Because remember, what we're trying to find is phi. Well, we have a relationship between z and phi, just by definition. Remember our conversion factors. Actually, I'm going to sneak it right in here. So that was kind of our side work to find the value for z. So here, I know by definition, z is rho cosine phi. Well, at this point where they meet, I know what the z value is. And I also know what rho is, because right there we're actually on the sphere. So on the sphere we know rho is equal to 5. Now notice what we end up with here is an equation that only has phi in it, so now we can figure out what that angle is at that point. If we divide both sides by 5 and do the arc cosine of both sides, and we can see that, of course, phi is pi over 4. So now we know z goes from 0 to pi over 4. Phi is generally the hardest of the bounds to find on these, as you will see. Now to get the entire ice cream cone, what does theta have to do? Theta has to go all the way around, so we would go from 0 to 2 pi. All right, from now it's just a basic integral if the bounds are even constant, so that one should be pretty easy for you to finish up. Let's take a look at a harder problem. In fact, let's do the one that we did for cylindrical. Let's convert something. Let's say if I told you to convert to spherical, just like we did before. Let's see, what the one I gave you was negative 2 to 2, negative square root of 4 minus x squared, positive 4 minus x squared, x squared plus y squared to 4. I think I put an argument in there. I think it was x dz dy. X. That x may be wrong, but we'll see. It doesn't really matter. All right, let's say that we wanted to convert this to spherical. Again, just like before, anytime you're going to convert something like this, it would be very, very helpful to sketch the region. I'm going to do this quick since we've already done it. We know this goes from z equals x squared plus y squared up to z equals 4. Remember, this is the paraboloid with a top up here at 4. And we do the entire region, because in the xy plane, the bottom half here is the negative square root of 4 minus x squared. The top is the positive of 4 minus x squared. And our last bounds, x goes from -2 to +2. So x covers this entire circle, y goes from the top and the bottom of the circle, and the z goes from the paraboloid up to the plane. So we get this entire volume. So how do we convert this to spherical? Well, to kind of help us out, I'm going to leave this here. I'm going to get these two out of here for now. It's going to be kind of helpful if we kind of take a look at a side picture of this, kind of like we did our ice cream cone. Now the side picture of this is a little bit different. It looks something like that. So if we're going to convert this, let me get started here. We're going to convert this to spherical. Let's take a look at what happens to rho. Remember, rho always starts at the origin and then heads out and hits the curve. The problem with this particular one, as we're moving, I'm actually doing this wrong direction. Notice what we're doing. We start and rho goes out and hits the paraboloid, but then at a certain point it starts hitting the flat surface on the top. Since rho hits two different surfaces, we have to set up two different integrals for this. Okay, so we'll figure out which one's which in a second. So let's go ahead and get the argument taken care of. Let's convert our x. We know x is rho sine theta cosine theta. Let me give me a little bit more room here. Then we know this was our little piece of volume, right? This is our dv right here. What is dv in spherical? It is rho squared sine theta d rho d theta plus. All right, we got to do the same exact thing for this integral. We're still going to have rho sine theta cosine theta. That's our x. Rho squared sine theta d rho d theta. Okay, so again, remember this is our x, and all of this is dv. This is our x. All of that is dv. Okay, so now we got to come up with the bounds. I know rho is first, but we've already decided rho is going to hit two different surfaces out of this. Well, what determines when we change surfaces? Notice if we spin around, that's not going to change which surface we hit, right? If we have some rho that comes out, if we spin that around, it's always going to be hitting the paraboloid, or if we take that one and we spin that around, it would always hit the plane. What determines when it changes is actually the angle phi, right? Because we start at phi equals 0 and we go down. So from phi equals 0 to whatever this angle is right here, I'm going to draw us another picture here. Same picture. Right there, at that angle phi, whatever that angle is right there, is when we change from the plane to the paraboloid. So let's go from 0 to something. That's going to be phi. Notice I started with phi. Let's see if we can figure out what that angle there is. Well, this is actually going to take a little bit of work, but again, just like we did before, that's when the two surfaces meet each other. So when do these two surfaces meet each other? Well, that's when z equals 4 and z is equal to x squared plus y squared. Or this is when 4 is equal to x squared plus y squared. All right, well, we're trying to figure out what phi is here. We could go ahead and try to solve that. But it's a little bit easier to do than a whole bunch of, let's take a look at our picture again, of plugging in spherical. Well, what do we know here? We know when these two meet, now technically it's this side over here too, that creates a circle of radius 2, right? That's when the two meet. That's the top piece of this, which means this side here is 2, right? We also know that that's the plane at z equals 4, so this side is 4. Remember, that's what we're trying to look for right there. Basically what we have is we have a right triangle with two sides of it. We have the opposite and the adjacent. So we can see that the tangent of that angle is 2 over 4, or the tangent of phi is 1/2. So phi is equal to the arc tangent of 1/2. Now I don't know what the arc tangent of 1/2 is off my head, but I know that this is going to give me a positive answer because that's going to be in our first quadrant, so that will work. So looking at our picture again, from 0 to the arctan of 1/2, that's when we're going to be on this is when we're going to be on the plane. Then, let's see, for the rest of it, what's it going to go from? Then from the arctangent of 1/2 down to pi over 2, that's going to be when we're on the paraboloid. So this is going to be from this angle here, this is the arctan of 1/2 to pi over 2. Okay, so we got kind of a lot of math. So what are we going to do on the plane? What does rho run from on the plane? Well, rho runs from 0 to that plane. Well, what's the equation of that plane? Well, the equation of the plane is z equals 4. Let's get this out here real quick. Got that taken care of. So on the plane, we know z equals 4. We know rho, z is equal to rho cosine phi. So rho is equal to 4 over the cosine of phi, or rho is equal to 4 secant theta. So rho always starts at the origin and heads out. So this is going to go from 0 to 4 secant phi. And then to draw this whole surface, we got to go all the way around in theta. So theta goes from 0 to 2 pi. All right, on our paraboloid, well, we know in our paraboloid, z is equal to x squared plus y squared. So what does rho run from? Again, it's going to run from rho equals 0 out to that paraboloid. So it's going to go from 0 to the paraboloid. But what's the equation for this? Well, we know z is rho cosine phi. X is rho sine phi cosine theta squared rho sine phi sine theta squared. Let's clean this up a little bit. Cosine phi, it's rho squared sine squared phi cosine squared theta. Rho squared sine squared phi sine squared theta. Now if you notice on this side, we can clean this up a lot because that both of those terms have a rho squared sine squared phi. If we factor that out, we end up with our Pythagorean identity. So this is just rho cosine phi, rho squared sine squared theta. We can divide out a rho because generally we're here. We know we're not at rho equals 0. We're at rho equals the paraboloid. So we know that's not the 0 case. So this is cosine phi is equal to rho sine squared theta. Remember, we're trying to figure out what rho equals on here. So if we solve for rho, rho is equal to cosine phi over sine squared phi, which is fine, but most textbooks aren't going to generally write that as a fraction. They're probably going to write this as, this is just a guess, cosine phi over sine phi times 1 over the sine of phi, which of course that's cotangent phi and cosecant phi. And by the way, if you left it like this, that would be perfectly acceptable. Okay, so rho runs from 0 out to the paraboloid. The equation for the paraboloid is rho is equal to cotangent cosecant. Cotangent phi cosecant phi. Now again, to map out this entire region, we're going to have to go all the way around. So theta goes from 0 to 2 pi. All right, as you see, this one wasn't nearly as easy to do in spherical because, well, we don't have a lot of spherical type shapes. We have circular shapes. That's why it was so much easier to do in our cylindrical coordinate systems. All right, remember when you go through to do anything in spherical, you look where rho runs from, where phi runs from. Again, that's the angle coming down from z, and then theta is the amount that you need to spin around the z-axis.